In this video lesson, I'm going to be looking at the cases of centripetal force. In my previous video lessons, I've taken time to explain that when the body moves in a circle, now moving in a circle, the motion could either be number one, uniform. In this case, we said the body is in a state of uniform circular motion. And the motion also can be said to be non-uniform. These are the cases I explained in my last videos on circular motion. For uniform circular motion, I said the body moves with a constant tangential velocity, constant speed, v. And since the speed is constant, let's say this is a case and the body is here. It moves and the direction of motion, I said earlier, is along the tangent at any point. So this is direction of the speed or velocity of the body, okay? And if the velocity is constant, then the acceleration of this body, that's what we call centripetal acceleration, is directed towards the center of the circle. Now, since the speed is constant, the radial acceleration, at, which is also directed the same way as the velocity, is equal to 0. Of course, for the body to have radial acceleration, it follows that the velocity must be changing because radial acceleration is also directed along the tangent to the circle at this point. So for uniform circular motion, the centripetal acceleration is not 0, but the tangential acceleration rather, is equal to 0. For non-uniform circular motion, the tangential acceleration is not equal to 0 for non-uniform. So what I'm going to be considering in this video is a case where a body is moving with a constant linear speed or constant angular speed or velocity. Okay, look at the case of a stone. This case now, a stone of mass m is rotated with an angular velocity omega by means of a string, by means of a thread or a rope of length L attached to it. Now you can see the cases here. This is a kind of a case of a body moving in a horizontal circle, because also have the motion of a body in a vertical circle. So what I'm considering now is the motion of this body in a horizontal circle. Okay, look at the case now, and this is the string. The length of the string is given as L. This is another diagram showing the body moving in this horizontal circle. Here's the stone of mass M. Now the length of this string becomes equal to the radius of the circle R. The length of the string is equal to the radius of the circle. And then the tension in the string, of course, if you they can demonstrate this practically. Just take a rope, tie one end of the rope to a stone and hold the other end and then wire it in a horizontal circle. You feel the force that is at least pushing towards you. That is the tension. So in this case of a stone moving in a horizontal circle, the tension in the string provides the centripetal force. Remember that centripetal force is a force that keeps a body that moves in a circular track so that this body does not slide off. It does not veer out of the circular track. So it is also directed towards the center, centripetal force, just like we have centripetal acceleration. Because from Newton's second law of motion, for acceleration, for a body to have an acceleration, it must be caused or produced by force F, which means this force F must be called the centripetal force, since this acceleration is centripetal. So this is responsible for the acceleration. And the centripetal force is also directed towards the center, this is my FC, of the circle. So in the case of a stone tied to a string and then whirled in an horizontal circle, it means that the tension in the string provides the centripetal force. So which means we can equate tension T is equal to centripetal force Fc, which is the same thing as mv squared over r. I think v squared over r is the expression for the centripetal acceleration. So that from this equation now, force is mass times acceleration. So that's why we have mv squared. It can also be given by m omega squared multiplied by r. But here, because I already said the length of the string is equal to the radius, so I can write it this way: mv squared over the length of the string, or I can write it as m omega squared times the length of the string. So this is tension in the string, which is also what provides the centripetal force necessary to keep this stone while in moving in this horizontal circle. Now let's kind of play a little with this equation. Now what do you have to see here? That suppose the speed is increased. Let's say with the course of rotating this stone, with a particular speed, let's say it's 5 meters per second, and then suddenly the speed is increased to 10 meters per second. As the speed increases, the angular velocity of speed also increases, because linear speed is equal to angular velocity of speed multiplied by the radius, which is also the length of the string. So if since the radius is kept constant, or the length of the string is kept constant, if you increase the angular velocity, the linear speed also increases. So when we increase the angular speed, that is, we rotate, we move, we while the stone faster, it means that the tension in the string increases. So if the string is not strong enough to provide the required tension, which also provides the centripetal force, it means that that string will break. Let's see, this is where it is now, and suddenly the rope or string cuts here because of the high tension. It means that the stone is going to fly off along the tangent at this point. So it flies off in the direction of the tangent at this point. So increasing the angular velocity, increasing the linear speed will also increase the tension in the string, and therefore increasing the centripetal force needed to keep the body in circular motion. So if the rope is not taut enough, it's not strong enough, it cuts. Okay, so that's what it means. And again, when if I have to keep that constant, it means that I have to reduce the length of the string. If I increase this, I don't want to increase the tension. Increasing the speed means I must decrease the length to keep the tension constant, or to keep the centripetal force constant. So this is the case of a body that is tied to a stone, for instance, in this case, tied to a string and wired in a horizontal circle. Now let's look at another case. Now here we have, consider this given system of masses in the uniform circular motion. Recall that this is just a string, and we have three particles, three small masses connected to this particle. We are going to find the respective tension, because the tension in this string, 1, 2, 3, provides the centripetal force needed to keep these stones moving, or this mass is moving in circular motion. Okay, so let's start with the last mass M3. The tension in mass M3, of course, let me call that T3, is due to this section of the rope from here to the end of this other end of the rope, where it is tied to this point here, point O. Okay, so but the tension in this other string, let's call it T2. Now T2 is countered, is opposed by tension T3, because these two forces were the same, because it's the same thing, the same string. So tension T3 is the tension in the string that is for mass M3. Then for mass M2, the tension in this string that provides the centripetal force that keeps M2 in motion is T2, which is opposed by T3. Okay, T1 is acting this way, which is opposed by T2. Okay, so I can say on mass M3, okay, the tension on mass M3, let me start with mass M3. For mass M3, the tension T3 is equal to M omega squared times R3. What's my R3? R3 is measured from M3 to the point of suspension of the string. Okay, to this point, this is my R3. R2 is measured from this point O to mass M2. This is my R2. Whereas R1 is measured from here to where I have mass M1 connected as R1. Now R1, R2 represents the distances, the distance of M3 from the point O, and so on and so forth. And when this starts rotating, the R3 becomes the radius of the circle of mass M3. Okay, so that's T3. Now for mass M2, let's see the tension. For mass M2, we have T2 minus T3. That provides the difference between these two tensions, provide the centripetal force. Remember, for the first case, T3 is the centripetal force that keeps mass m3 in circular motion. So the difference between the two of them equals the centripetal force, which is given by m omega squared ROT. So this is the centripetal force that keeps mass m2 in circular motion. It is given by the difference between two tensions. Now we can determine tension T2 so that T2 becomes equal to m omega squared R2 plus T what? 3. Remember what T1 is. So sorry, this is T2. So that my T2 equals m omega squared R2 plus m omega squared R3. Okay, so you can see that the tension T2 in this other string, this part of the string, is greater than T3 because T2 is the sum of this term and this term. Okay, how about T1? Now on mass M1, what is that centripetal force that keeps M1 moving in a circular motion? Now the centripetal force on M1 is the difference between T1 and T2. So my T1 minus T2 is equal to m omega squared R1. That is what provides the centripetal force. Of course, this expression represents the centripetal force that keeps the mass m1 in circular motion. So that my T1 is equal to m omega squared R1 plus T2. I can substitute the value of T2 from the above equation so that I have m omega squared R1 plus what was my T2? M omega squared R2 plus m omega squared R3. So I can factor out, sorry, this is M1 so that I don't make a mistake there. This is M1, this is this is M1. This is for, I should have included the masses. This is M3 because I'm dealing with mass M3. So for this one now, I have here M2. Okay, so plus T3. So this is M3, this is M2. Let me include the masses to avoid confusion. This is M1, and this is M1, M2, and M3. Okay, so this how to write the expression for the tension in the string. And recall that the centripetal force is the difference for M1 is the difference between T1 and T2, the two tensions, T1 and T2. And for M2 is the difference between T2 and T3. And for mass M3, the centripetal force is equal to T3. So that's a case of determining the tension in the string.